distribution in multiple bonds, including resonance structures. If we look first at hydrogen. So hydrogen is a single bond. If we were to look at two hydrogens bonded to each other, we would notice that, let's redraw these nuclei, we would notice that the concentration of electrons would be probably somewhere in between those two nuclei. Okay, so when the electrons directly between nuclei in a bond, this is what we refer to as a sigma bond. All bonds include one sigma bond. Okay, so if it's a single bond, it's going to have at least one. If it's a single bond, it will have one sigma bond. If it's a double bond, one of the bonds will be one sigma, and then the other one will be what we call a pi bond. If we have a triple, we will have one sigma bond, and we will have two pi bonds. Okay, so what are pi bonds? Well, if we look at something else, like let's say we have ethylene. Ethylene has a double bond. One of those double bonds is sigma, the other is a pi bond. Now we know if we look at this carbon to carbon that it's most advantageous for them to share electrons directly in between. So there's going to be the orbital overlap, and so there'll definitely be a density of electrons hanging out in here. However, if you remember from Pauli exclusion principle, we can only have two electrons of opposite spin occupying one orbital. We know that electrons like to repel each other. So what happens with the electrons that are in the second bond? Well, what happens is we end up with, so this is remember a single p orbital has this water wing shape. So what will happen is that these p orbitals, since they're sharing with just another p orbital, they don't hybridize. And so the electron distribution, if these two are kind of overlapping, the electrons distribute themselves both above and beyond. That kind of would look to us like a triple bond, but that's just a double bond. So it's this, all of this overlapping in here, from here to here, that forms one pi bond. It is p orbital overlap. Now, if we go and we redraw some stuff, so if you remember, this is carbon, this was one hybrid. So this is the overlap, this electron density is the overlap between the hybrid of this carbon. And remember that we still had, there's these hydrogens, so there has to be a hybrid orbital here and a hybrid orbital here with our hydrogens. And those hydrogens were just good old S's. a hybrid orbital here, and a hybrid orbital here. So if you remember, so this takes a little bit of thinking. Remember that carbon had S and P's here? So 1, 2. Now, these three are hybrids in order to form this sigma bond. And this sigma bond and this sigma bond, we'll just focus on this carbon. So for that sigma bond and that sigma bond, these three orbitals had to hybridize. So we have sp. How many p orbitals hybridize? Only 2, sp2. Now, because these p orbitals are just bonding with other p orbitals in this shape, and because of the way the electrons have to distribute themselves, those p orbitals don't hybridize. So this is why this forms 3 sp orbitals and just one old good p orbital, which overlap to be the pi bond. Now, what happens in the mess of if we have a triple bond? So we have as in the case of this molecule. So one of these bonds has to be a sigma, and so the other two are going to be pi's. How is this going to look now when we draw this thing? So again, we're going to have, because of this hybrid orbital and this hybrid orbital, we're going to have some electron density in here. And that again is our sigma. Now I want you to imagine like you have a sheet of paper. Let's say you're holding that sheet of paper up vertically and you drew p orbitals vertically. So you would have sort of this parallel up here this way. So that would be the pi bond from the vertical p orbitals. Now I'm kind of going to restart, but imagine these two things existing together. So you also have, so you've got the sigma, you've got pi bonds from that first set of p orbitals. Now imagine you now take that piece of paper, or you got another sheet of paper where you had p orbitals drawn on it, but you turned that paper now horizontally. So now say you have p orbitals going out this way. So now the electron density, if you imagine these p orbitals overlapping, so the distribution would be hanging out this way. Okay, so if you could kind of imagine this all smushing together, so you've got these p orbitals going out horizontally, and then that's your third pi bond. So you've got sigma in blue, you've got your first pi bond in red, and you've got your second pi bond in green, also going in parallel. What happens now with resonance structures? And how does that electron distribution look? Well, if we look at something like our benzene ring. So remember that benzene, I'm going to just draw the simple like organic chemistry thing here. So remember we have the alternating double bonds here. So let me first just draw what the pi bonds might look like. I'm going to leave out the sigma bonds. I'm just going to draw the pi bonds for that first structure. So we've got a carbon, a carbon, a carbon, a carbon, a carbon, a carbon here. So each of those carbons has p orbitals involved in the bonding. So basically, if I were to look at this first diagram here, you would see the overlap, the electron density here, here, and here. And remember that there are, I'm just going to draw a line. Remember that there's a sigma bond here, sigma, 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 connecting everybody up. Now, if I were to draw the other version, so now I have, again, we have these p orbitals, water wings, so now showing this bond, overlap here and here, electron density here and here, electron density here and here. And then of course, before all that, I should have said that there are sigma bonds between all those carbons. However, remember that both of these can kind of exist, and electrons just go wherever they are needed. So what I could do instead, and I don't know why my bamboo pad or my tablet here is acting up, might be low on power. So if I draw this again, one more time, what really happens is if we have all these p orbitals, is that the electrons become delocalized. So instead of electrons just hanging out here in that double bond, or deciding to hang out here in this double bond, what really happens is the overlap happens all the way around. And it happens all the way around on the bottom too. So what we really have going on is like a double donut, a parallel double donut. I like it. A double donut because these electrons become delocalized. So they're really kind of hanging out with all of the atoms instead of just staying in one pi bond between two specific atoms. If we were to re-talk about